Okay students, I hope you are all well and healthy and ready to learn the new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center Navsari in Civil Engineering Department as an assistant professor. So I am going to teach you the design of structures. In this subject, today we are going to learn one-way continuous slab. Okay, so shall we start? Good. Okay, students. So here is an example. A typical floor plan of a building is shown in figure as following data. So in the example, we have one floor plan and some given data. So what is the data is here? Multi-story rigid joint frame. Number of story 4. G plus 3 means 4 floor, ground floor, first floor, second floor and third floor. Floor height 3.35 meter. Height of plinth 1 meter above ground level. Imposed load. There is a roof live load, floor finishing live load. This data is given. So this data is given. So we are using this data for design a G plus 3 building. And these are the material we have to use: M20 and Fe415. Unit weight of concrete 25 kN per meter cube is given. And we have to design a multi-story building using limit state method based on IS 456 2000. Data is given. This all data is given. So let's check the floor plan. So I'm going to analyze this floor plan. Just look at here. S1, 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 S2, S2, S3. These all are S1. Okay, these all are S1. So in this example, in this lecture, we are going to learn the design one-way continuous slab. Okay, so we are going to design a step by step. First of all, G plus 3 building, whole building cannot design in a one lecture. So we are going to design first one-way continuous slab, second two-way continuous slab, third continuous beam, then after column, then after footing. So I am going to explain step by step all the things. Okay, first of all, understand the typical floor plan. Okay, so look at here, this symbol, this symbol, this S1, S2 and S3 is a slab name which given by a structural engineer. Okay, S1, S2 is not defined by a one-way slab, two-way slab. It's just a slab name which given by a structural engineer. But this figure, this symbol, this and this symbol define a one-way slab and two-way slab. Okay, so by this symbol you can say there is a main reinforcement on the shorter span. Okay, this symbol represent a main reinforcement, so you can say main reinforcement at a shorter span, and this symbol represent main reinforcement at both direction. Okay, the given data, look at here, these are the okay, these are the slab clear span of a beam. Okay, 3 meter. So I can say there is one slab is S1 is here, so one is 3 meter, second dimension is 6 meter, so 6 by 3 is equal to 2. So it's 2 means it's a one-way slab, but it's continue. Why? Because it's connected with each other. So if I want to design a one-way slab, a single panel, I can design easily. But here is connected, is continue. So what happened? If your slab is continue, your moment is distributed. moment will be distributed on the whole panel. Means your moment here, maximum moment will be distributed here. This slab moment will be distributed here and here. This slab moment will be distributed here and here. Okay, so this moment will be distributed, and while the moment is distributed, our slab design will be less. Okay, for continuous slab, this understand your moment will be distributed. Okay, understood? So in this lecture we are going to design one way continuous slab. Start. Okay. It's an example, it's a typical floor plan, we understand all the things. Yeah. Design a slab at typical floor level. We have a three type of slab. One is S1, S2, S3. We are going to design one way continuous slab in this lecture. In the next lecture we are design S2 and S3. Okay, first of all we have to find out effective depth. Effective depth equation, length by depth ratio is equal to 26 into mf. How this possible? 26 into mf. IS 456 2000, page number 37 and 38. Let's check. IS 456, page number 37. There is a page number 37. Okay, control deflection equation is here. Control deflection, and look at here, the vertical deflection limit generally be assumed to be satisfied provided a span of depth ratio are not greater than the value obtained as below. Span to depth ratio for control a deflection, span and depth ratio. Okay, for a control a deflection, what we have? We have a span. We have a span of slab which is 3 meter is given, but we don't have a depth, a thickness of slab. So we can find out what? A depth by whom? Control a deflection. So span and depth ratio we can find out, and by a span value we can find out depth. Okay, L by D is equal to 26 mf. So how we get 26? How we get 26? Look at here. The basic value of span effective depth ratio for a span up to 10 meter. Up to 10 meter. What we have? Less than 10 meter means up to 10 meter, 3 meter and 6 meter. So if your slab is cantilever, 7 into mf, 7 into mf. If your slab is simply supported, 20 into mf. If your slab is continuous, 26 into mf. What we have? One way continuous slab. So 26 into mf. Mf means modification factor. How we found a modification factor, it will discuss earlier while we design one way slab, two way slab and beam. Okay, so these are the here how we get 26 into mf. 26 into mf, and right now we have to find out mf, modification factor, from page number 38. 7, here is 38, here 38. Okay, so we have a table here, we have one graph is here. The x direction is a percentage of tensile reinforcement, y modification factor, and here is some fs value. Okay, then how we found fs by this equation, 0.58 into fy. For the fs we have 0.58 into Fy. What is Fy? Fy is steel grade, which is 415, which is given in the example. We have to use 415 grade of steel. So Fy 0.58 into 415. So approximate value is 240 point something. 240 point something. So we can take Fs is 240. Fs is 240. So let's check. We have a graph Fs 240. Yeah, look at here. Here is a graph Fs 240. Okay. Here's a graph Fs 240. Okay. So by this graph we can find out modification factor. But one more data is missing. Percentage of tension reinforcement. Percentage of tension reinforcement, which we found later. Okay, while we design a slab, we found it per pt, percentage of tension reinforcement. After the end of the moment, find a bending moment. Then after we have to find out percentage of tension reinforcement. But we need a modification factor right now because we need a slab thickness. So what we do? We assume pt 4.4%. We assume means assume 0.4 percentage pt, percentage of steel 0.4%. We assume this data. You can assume anyone, 0.5, 0.6, 0.2, 0.3. Okay, we can assume any data but not more than 2%. Okay, not more than 2%. So 0.4% we assume data. Okay, so while we assume 0.2, look at your percentage of tension reinforcement. Here is 0, is 0.4. So 0.2 in between 0 and 0.4, where? Right here. This line represent a 0.2. At the center means first line is 0, second line is 0.4. So means the first line, which is in the center between 0 and 0.4, is 0.0, sorry, 0.2. Okay, and Fs line 240 and 0.2 meet at 1.6 more. Okay, 1.6 and more. So we assume we found mf is 1.35. 1.35. We found out mf 1.35. If you don't have is code, is 456, page number 37, if you don't have, then we can find out mf 1 divided by 1 plus 0.625 log pt. Log pt. Pt means percentage of steel at the tension reinforcement. What we assume? 0.4. Put this value in this in equation and find out mf. Check this data. Okay, I'm going this mf data to find out yourself. Okay, do it by yourself and make it perfect. Okay, then after ld, put the all value. L is 3000 divided by depth is equal to 26 into 1.35. 1.35. So D is equal to 85.47 mm. We found a thickness of slab, effective thickness of slab 85.47 mm. Okay, this we find out. But what we provide? 90 mm. 85.47 is minimum. We cannot provide 70 mm or 80 mm, 80 or 770 mm. So we provide 90 mm because this is the minimum value. 85, we cannot provide less than 85.47 mm. Okay, so we provide more than 85.47, so 90 mm. So now we have to effective depth. I need overall depth. Overall depth equation, small d plus 5/2 plus clear cover plus 5 by 2 plus clear cover. So we have to assume a data, assume 10 diameter bar. Okay, I assume 10 diameter bar to provide in the slab. So small d plus 5 by 2 plus clear cover. Clear cover is 20 So overall depth is 115 meter. How we find out this? Check it here. It's a slab. Okay. Okay. What we find out? We find out effective depth here, which is 90 we provided. But what we need? We need overall depth. Overall depth. Okay. So we have to do 90 is effective depth plus 5 by 2, which is provide 10 diameter bar and clear cover. So we find out overall depth 115 meter. Okay. Understood? Next we have to find out effective span. We have to find out effective span. How we find out effective span? Effective span, why we need it? Because we have to calculate the data by design bias effective span. So we have a two condition here. First we have to check out center to center of span 3 meter, width of support 230. Then we have to clear span 270 These are the given. Clear span. We find out this. How? Let me explain. It's your slab. Okay. It's of slab. Okay. And this is the support. This is the support. And we have the center to center 3000 What we need? We need a clear span. So what we do? 3000 minus 230. So value is 2770 These are the clear span 2770 Okay. So 2770 is the clear span. So IS 456 2000 page number 34. We have continuous slab. So this condition is follow for the find effective span. 1 by 12 into clear span. 1 by 12 into clear span. Why this data is here? Look, let's check. IS 456. Effective span. First is simply supported beam. Second, B continuous beam or slab. Okay, look at here. We have continuous beam or slab. We have the different condition for the find out effective span. Read it. A case of continuous beam or a slab if a width of support is less than 1 by 12 of clear span. Less than 1 by 12 of clear span means clear span we have a 2770. Clear span 2770 divide by 12, and this value, if this value is less than support width. Support width means what? Here, this width is 2770 is clear span divided by 12, and this value is less than or equal to 230 support span. Okay, then we have to follow 22.2a clause. 22.2a clause. So here is 22.2 effective span, and a here is a clause. So simply supported slab condition will be follow. Simply supported slab condition will be follow here. So 1 by 12 into clear span. So value is 230.83. is nearer to 230. It's nearer to 230. So we have to follow simply supported slab if condition. Simply supported slab condition. So first condition is clear span, and second is simply supported of center to center of support. Clear span plus effective depth. So 2770 plus 90 is effective depth, which we provided 28 2860 mm, and center to center 300. By these two value we can find out effective depth. Whichever is smaller we take it as a effective depth. LE 2860 mm, 2860 mm. So we have the slab dimension, we have all slab dimension, depth, effective span, and all the data. So right now we have to find out load calculation. So for the continuous beam, we have continuous beam or continuous slab. We have to calculate dead load and live load separately. Okay. In the earlier calculation, we find out dead load, then after live load, and summation to all the load here. Okay. But in the continuous beam or continuous slab, we have find out dead load differently, live load differently. Okay. Why we do this? Let's check. I will explain it later. So first of all, we have to find out self weight of slab. Self weight of slab. So same condition here. Same condition here. Slab is divided into 1 meter strip. We assume 1 meter strip of slab. So all the load we will find out on the 1 meter strip. Okay. So self weight of slab. So 1 is 1 meter strip. 0.115 is the thickness, overall thickness of slab, into 25. 25 is the unit weight of concrete, which is given in the example. Which is given in the example. So self weight of slab is 2.875 kilonewton per meter. 2.875 kilonewton per meter. Okay. Then after floor finish. Floor finish 1 kilo per meter square is given in the example. Floor finish is 1 kilo per meter square is given in the example. Check the example. Let's check. Number of story, numbers of height. Here. Floor finish 1 kilo per meter square. Live load 4 kilo square for the floor finish is given. Okay. So this data is given. So we use this data. So floor finish 1 on 1 meter strip. So 1 kilo per meter square. Total dead load 3.875 kilo per meter. And dead load is factor load 1 multiplied by 1.5. So 5.81 kilo per meter. These are the total dead load which applied on the one-way continuous slab. Okay. Then of the live load. Live load is given 4 kilo per meter. 4 kilo per meter in the example. Look at here. Here. The floor finish is 1 and live load is 4 kilo per meter square. These are the given in the example. Then of the total live load, factor load 1.5 into 4, so 6 kilo per meter. Okay. This load we find out. Okay. We find out factor dead load 5.81, factor live load 6 kN per meter. So we have to calculate bending moment calculation. Bending moment calculation. For the bending moment calculation, we need dead load coefficient, live load coefficient. And how we find out, we made this table, and how we have to follow this data we will discuss right now. Okay. I will explain it by a figure. Wait a second. Okay, I am going to draw one beam. Here is a beam, here is a support. So continuous beam, we have a multiple support here. Okay, and UDL load. Okay, these are not matched with the example. These are I'm going to explain by some. Okay, these are not matched with the example. Okay, support A, B, C, D, E, F, G, H, I. Okay, H, I. Then after we have to dead load, live load coefficient, dead load coefficient, live load coefficient. Okay, so we can find out from the IS 456 page number 36. Okay, table number 12. So here is a table number 12, bending moment coefficient. Table number 30 gives the shear force coefficient. Shear force coefficient. For find out shear force, we have to use table number 30, but we need a bending moment. So we have to follow table number 12. And we have the type of load, dead load and live load. Both are different coefficient. So that's why we have to calculate dead load and live load differently. Okay, separately. Okay. Then after span moment and support moment. Span moment and support moment. So these are the coefficient here at a span, at a support. So at a span, first is a near middle of end span, near middle of end span. Okay, what we dead load have 1 by 12 and imposed load means live load has 1 by 10. Near middle of end span, near middle of end span. So these are the near end span. This is the end span. These both have end span. So dead load is 1 by 12, 1 by 10 plus 1 by 12 plus 1 by 10. End span in the middle of end span. So at F we have a coefficient 1 by 12 and 1 by 10. These are the dead load and live load coefficient. Second, at the middle of interior span, at middle of interior span, 1 by 60 and 1 by 12 at the middle of interior span. So here is the interior span at the middle, dead load 1 by 60 plus 1 by 12 plus 1 by 60 plus 1 by 12. These are the span moment is completed. Span moment is completed. So we have the support moment here also. Support moment at the support next to the end support. At the support next to the end support. Dead load coefficient minus 1 by 10 and live load coefficient minus 1 by 9. Okay. At the support next to end support. At the support next to end support. These are the end support A and E. Next support is B. So minus 1 by 10, minus 1 by 9, minus 1 by 10, minus 1 by 9. Okay. So these are the first case is completed. Second, at other interior support, minus 1 by 12, minus 1 by 9. At other interior support, so these are the interior support, minus 1 by 12, minus 1 by 9. Okay, then these are the end support. End support we have to 1 by 24 and 1 by 20 plus, no sorry, not plus, minus. At a support always be a minus, 1 by 24 minus 1 by 20. Understood? So these table is completed for the dead load and live load coefficient. Okay, so how this table is created you can understand easily. Okay, so these are the coefficient here. First of all, we have to find out bending moment at F. Where is F? At the center. So bending moment at F, we have dead load coefficient 1 by 12 into 5.81. It's dead load. 5.81, it's a dead load. Okay, into 2.86 whole 2.86 square. These are the effective span 2.86. Okay, so multiply the all data. These are the 1 by 12 is coefficient, 5.81 is a dead load which is applied on the slab, 2.86 is the effective span, and multiply by 3.96. These are the moment. This is the moment. Newton into meter. Okay, this is the moment for the dead load, and second is for the live load. Coefficient 1 by 10, 6 is a live load, 2.86 effective span, so 4.91 kilonewton per meter. These are the live load moment, kilonewton into meter. Second, at B means at a support, B means at a support. So we have the, okay, so minus 1 by 10 is the coefficient for the dead load at the support. 5.86 is the dead load. 2.86 is a span, effective span. So value is 4.75 kilonewton into meter. 4.75 kilonewton into meter. Then after live load, minus 1 by 9 it's the coefficient of live load at the support. 6 is the live load. 2.86 is effective span. So value is minus 5.45 kilonewton into meter. These are the moment, live load moment. Okay, and here is a total moment, summation of these two. Bending moment at F, total moment, summation of these two value, 3.96 plus 4.91. So total moment is 8.87 kilonewton into meter. So I am going to design a one-way slab. If I am going to design this slab at F, we have to use bending moment at F is 8.87. Okay, so this is the bending moment, and here is the bending moment at support at B. Summation is 4.75 plus minus 5.47. So total load is minus 10.20 kilonewton into meter. Okay, these are the moment is given. You can find out for the all at G at C. So I'm going to directly design a main reinforcement. You can follow all the coefficient for the design, all the slab, but I'm going to explain only one slab at one support, one slab and one support. So first of all, main reinforcement at F, mu we find out 8.87 kilonewton into meter. 8.87 kilonewton into meter. So mu upon bd square, 8.86 into 10 raised to 6. 8.86 into 10 raised to 6 divide by 1000. For the 1 meter strip we assume effective depth is 990 whole square. So mu upon bd square 1.095. 1.095. Okay, this by this value we can find out pt. We can find out pt from SP60 page number 48. From SP60 page number 48. We have to use FCK20. Here FCK 20, FY 415. Okay. MU upon BD square. We have a MU upon BD square is 1.095. So 1.1, 1.095. So here is 1.10, 1.10. Fy is 415. So our value is 0.327, 0.327. So PT is 0.327. I use 0.325, 0.325. So find out AST, PT by 100 into B into D into B into D. PT is 0.325 divided by 100 into 1000 into 90. So AST is 292.5 mm, 292.5 mm. And here is provide 10 mm diameter at 260 mm center to center. How this find out? I can write down directly. I am write down these values directly. So I can explain. Here is AST is 292.5. AST is 292.5 mm square. This AST is given 292. Okay. And small AST, we assume 10 mm diameter, AST is 78.52 mm square. So we have find out spacing in the slab. Small AST divided by capital AST into 1000. Put the all value here and you can find out spacing. You can find out spacing. So provide 10 mm diameter bar at 260 mm center to center. This we provided. Okay. Bend up alternate near support. Bend up alternate bar near support at a board support at A and B. Board support. So our slab is design completed. Slab design completed. But we have to design at support. So at B. At B. Okay. New 10.20 kilonewton into meter. This is find out. So mu upon bd square 10.20 into 10 raised to 6 divide by 1000 into 90 whole square 90 whole square. So value is 1.26. 1.26. PT is 0.35 percentage. 0.35 percentage. Okay. So AST 0.38 divided by 1000 into 100 into 90. So AST is 342 mm square. 342 mm square, which is required at B. Okay. So our requirement is 342 mm square. Okay. Slab at the support we require 342 mm square. Okay. But there is one condition here. Look at here. It's a slab is support A, is support B, here is support C, here is F, and here is G. So at A moment find out, V moment find out, at a C moment find out, we design F and we design the G. But one more condition here, our slab reinforcement. Our slab reinforcement provided like this. So I can say I am design the F and I am design the G. So 50% is the reinforcement from F. 50% reinforcement from F and 50% reinforcement from G at support B, at support B. Okay, at this condition, at by this condition, I can say 342 mm square is required at B. At B, 342 mm square is required, but 50% from F and 50% of G already at B. 50% reinforcement from F and 50% reinforcement from G. This reinforcement is already at support at B. So we have to subtract this value. So we have to subtract this value. So here AST from F 50%, 304 302 divided by 2. So 51 151 mm square is already at support B from F. Okay, and AST 50%, 239 divided by 2 F from G. So value is 119.5 mm square. So total is 151 plus 119.5. So still already available at B is 270.5 mm square. This reinforcement already at support B. Okay. So how we find out G data here? Reinforcement G, same format here. Mu upon BD square, PT, AST. So we found out at a G, G slab is design. So 239 mm square. Okay. So these are the data here. So at the support we have a 270.5 mm square is already at support B. Okay. So we need extra reinforcement. 342 mm square we require 270.5 mm square is already at B. So we need extra 71.5 mm square. We require only 71.5 mm square. Okay, so consider 8 mm diameter bar, small AST 50.26, spacing 701.95. So provided 70 mm as extra top reinforcement bar at support. But what length we provide? At which length? Okay, look at here. Is F is length is fixed, G length is fixed, but at the B we need some length here. We need some length. So what is length? L by 4. This length is given in the IS code. Okay, so we need L by 4. 2860 divided by 4. So 71.5 mm on each side of the center. Okay, so what we need at the center? We find out required reinforcement at the support. For the support design, we'll find out required reinforcement is 342 mm square, but from the both slab at F and at a G we have a 50% reinforcement already on the support. Already 50% reinforcement from F and from G is already on the support. So we have to neglect this value is summarize, subtract this value. So 302.302 is F reinforcement and 239 is G reinforcement. Divide by 2, 50% means divide by 2. So 151 mm square is from F and 119.5 is from G. So at a B we have already 270.5 mm, 270.5 mm square is already at B. So we need extra is 71.5 mm square. So what we design? We design for the 71.5 mm square. We require only 71.5 mm square reinforcement at support. Okay. So 8 mm diameter bar we provided. So spacing is 701.98 mm. 701.98 mm. So our spacing is we find out. Okay, look at here. I can explain it very in detail. Give me some time. It's your slab. Okay, It's your slab, and this is the, you can say, this is the beam or support. Okay, I say it as a beam. What we find out? We find out spacing. Spacing is 700 mm. Okay, so I can provide a reinforcement at some spacing. Okay, which distance is 700 mm. But which length, what length we need, here. Okay, I cannot provide a reinforcement like from here to here. I cannot do this. Okay, so what I did L by 4. L is effective span of slab is 2860 divided by 4. So this value we find out a length of reinforcement, which is 71.71715 mm on each side of the center. Okay, so this support completed, slab completed. Here is at C, same condition here. Look at here. So our one-way slab design is completed. Okay, here is a cross section. Here is the effective depth 90, 100 mm, 10 mm diameter at 60 mm center to center. Here distribution still we can provide here. Look at it, distribution still. Provide a minimum 0.12%. 0.12% minimum distribution, still we need provide 0.12% of cross section. So 0.12 into 100 divide by 100 into 1000 for the 1 meter strip, and overall depth 115. So provided 6 mm diameter at 200 mm center to center as distribution steel. Okay, let's make some drawing. Okay, so reinforcement is laid like this. Okay, same from here. Okay, so this type of reinforcement laying down, and here is a distribution still. I'm going to draw a rough diagram. It's not a perfect, it's a rough. Okay, so write down here 10 mm dia at 260 mm center to center. Okay, here distribution still 6 mm dia at 200 mm center to center. Okay, next here at a support B, 8 mm dia at 700 mm center to center. This two type of condition is fulfilled. Then of the effective depth D is a 90 mm, clear span 2770 mm, effective span 2860 mm. So once slab is completed, all the slab design will be by yourself. Okay, in this example I can explain in this detail. Wait a minute. Okay. So look at here, I am designing only one slab and one beam. So you can design this slab, this beam, this slab, this beam, all the data here. If I'm completed one slab, you can complete all the S1 slab, one way slab here. So keep practicing and learn one ways continuous slab. In the next lecture we discuss S2 and S3, and then after we starting a design continuous slab, and last one is column and footing. So G+3 building all will completed in these parts. Okay, so take care and we will meet soon as